The history of our ocean starts with the birth of our solar system and planet Earth. According to the nebular hypothesis, all bodies in the solar system formed from an enormous cloud composed mostly of hydrogen and helium, with only a small percentage of heavy elements. This cloud of gas and dust is called nebula. Here is a beautiful image of a helix nebula captured by a combination of 4 telescopes from NASA. And it shows a white dwarf star that formed in the center of the nebula. This image is about 4 light years across. The nebular hypothesis describes 3 stages of formation of our solar system. It begins with the contraction of the nebula under its own gravity, followed by the formation of a spinning disk. The disk's mass is concentrated in the center, where the sun formed. As the nebular matter that formed the sun contracted, small amounts were left behind in swirling eddies. These materials in the eddies were the beginning of the protoplanets and their satellites, which later consolidated into the present planets and their moons in a process called particle accretion. The process of particle accretion is similar or analogous to the accretion of dust under your bed. Take a look. Have you vacuumed recently? When you don't, you can see those balls of dust growing under the bed with uh, dirt and dust just forming those rows of, of, of dirt under your bed. And that is a way in which particles stick to each other, forming a clump. So, this particle accretion is the process that developed our planets with the small amounts that were left behind from the formation of the sun. These small amounts that were left in these swirling eddies that you can see here in this diagram formed the protoplanets and then consolidated into our planets. Here is a more simpler diagram that describes the nebular hypothesis and the formation of our solar system. Let me point out that this nebular hypothesis was proposed by a scientist named Pierre-Simon de Laplace in 1796. Laplace also proposed the dynamic theory of tides, as you will learn later in the course. He also described the contraction of the cloud into a spinning disk. And he pointed out the forces that developed the fragmented the disk. So once the centrifugal force equaled the gravitational force of the star in the center, the disk fragmented into the rings. And from these rings, the planets condensed. So, how old is our planet? How long ago did this happen? Here are some options. By the end of this video lecture, you will have the answer. Another question for you. Did our planet look like today's planet? Did it have an ocean? Did it have an atmosphere? Did it have continents in this exact same configuration? Did it have life? It turns out that Proto-Earth looked very different from Earth today. Its size was larger than today's Earth, and there were neither oceans nor any life on the planet. During this early stage of formation, many meteorites and comets from space bombarded proto-Earth. In fact, there's a leading theory that stated that the moon was born after a titanic collision between a Mars-sized planet and proto-Earth. Earth's surface was heated by these meteorites and asteroid impacts, but also by decaying radioactive elements. These are elements that have an unstable nucleus, which can decompose spontaneously or decay into a more stable configuration and emit energy or heat when doing so. Examples of radioactive elements include uranium-238 that can decay into thorium-234 when 2 protons and 2 neutrons are removed with an alpha particle. Other examples of radioactive elements are carbon-14, which can decay into carbon-13, or potassium-40 decays into argon-40, rubidium-84 decays into strontium-87, among others. Radioactive decay still emits about 50% of heat given by Earth. The third and last step of Earth's formation is called density stratification. On the early Earth, heat generated at the surface by the bombardment of space debris and heat released internally by the decay of radioactive elements was so intense that Earth's surface became molten. Once Earth became a ball of hot liquid rock, these elements were able to segregate according to their densities in a process called density stratification. Let's recall that an object's density is determined by comparing mass for volume. If you compare a rock and a cork, which have the same size, they have equal volume, but which one is heavier? The rock, because it has more mass. Thus the rock is denser than the cork because it has more mass in the same volume. Liquids have density too. This image shows how liquids of different densities settle down in a cup. The liquids with highest densities, in this case honey, will settle on the bottom of the cup, and the liquids with the lowest densities will settle on the top. During the density stratification of Earth, gravity pulled the heavier and denser elements, such as iron and nickel, to Earth's core. The lighter materials, silicon, magnesium, and oxygen-bonded compounds, rose towards Earth's surface, forming Earth's crust. The lightest materials stayed over the atmosphere. This diagram then summarizes the steps of density stratification in Earth's formation. Step 1, where Earth was formed by the accretion of cold particles within the spinning and flattened cloud of dust and gas. Step 2, Earth's surface was heated by meteorites and asteroid impacts, but also by radioactive elements. And step 3, density stratification, which led to the formation of the inner and outer core with the heavier, denser elements, the mantle, and the crust. So, Earth's birthday is considered when the crust was formed. The Jack Hughes zircon crystals from Australia are the oldest known crust material. Here's a picture of that crystal. These are dated to be 4.4 billions of years old. And it implies that a significant that continental crust must have formed on Earth early on, perhaps 4.6 billions of years ago. So these crystals are from Jack Hills in the western part of Australia. Now there's also evidence from dating space rocks left over from the formation of the solar system that indicate that Earth is about 4.6 billions of years old. With all this evidence, Earth's birthday is considered to be at 4.6 billions of years ago. That's how old is our planet.